Hello, everybody. My name is Paul Montin. This is joint work between me and colleagues from Penn State University and the Ohio State University. The topic of today is automatic counterfeit object-oriented programming attacks. And basically what we're going to show is a technique on how to automate attacks with the goal to show and give insights to people who want to protect against those type of attacks, see on which features they rely and derive more knowledge on how to protect against this type of attacks. So a little bit of background. As you might know, there are a lot of open source applications and they all have a lot of vulnerabilities. For example, Google Chrome, um, Edge, or Firefox. So every day, a lot of vulnerabilities and CVEs are reported by the National Vulnerability Database or by NIST. And these vulnerabilities, some of them can be exploited for this type of attacks in order to hijack the control flow of the application. This is why we see more and more bug bounty programs like this one from Google. And all major tech companies are actually involved in this space, providing programs and also um, bounties in case people can find these bugs and reproduce them in order to create this type of attacks. So these are a prerequisite, and because these bugs will not soon go away, we will have this type of vulnerabilities. And of course, the attacks will be present, and we see more and more flavors of them. So if we look into the CVE database, in total currently we have around 161,000 reports there. And from this one, 29,000 are arbitrary code executions. So roughly 1/5 of all the reported errors there are arbitrary code executions. And these are used mostly for crafting this type of attacks. And this is why it's super important to look at this topic, to study it in more depth, to learn in order to come up with solutions in order to protect against this type of attacks. But in order to understand how we can protect against this type of attacks, we should first learn how these attacks work in order to devise solutions which work against this type of attacks. So there are control flow hijacking attacks, which basically hijack the control flow of the program. So basically, it doesn't run as intended. And there is a plethora of defenses against them. So people published in the last years many defenses which work and which prove to be very efficient. Then we have, as a second branch, data-only attacks, which don't hijack the control flow of the program, but manipulate data in the program and basically achieve the same goal. And in this work, basically, we focus on control flow hijacking attacks and on COP-like attacks. So basically, there is this counterfeit object-oriented programming attack, and we automate it with our own approach. And we will see in detail how we do this. So next, about our methodology. So as you can see in this figure here, this is the whole attack construction pipeline. In a nutshell, we have CFI policies, which we use. Then we have the binary code of the vulnerable application. Then we have the ASL attack specification, which is basically our language for specify the attack. And these are CFI policies which we use in order to insert in the programs and to assess if the payloads and the attack which we built are able to bypass these attacks. So basically, the binary is fed into our front end, and then based on the ESL specification, so this is the code attack recipe, semantic search is done on this binary, and then we have we search for the call target. So basically, these are virtual functions and pointer-based function callees. And then based on this CFI policies, we apply them. And then essentially what we get, it's a reduction in the number of call targets because the CFI policies prevent that people can misuse them. Then we look for all kinds of dispatchers. Dispatchers are places from where functions are called. So for example, an object is calling a virtual function. These are dispatchers. Then we do so-called gadget simulation, where we simulate what the gadget actually does in memory. And then at the same time, we build this chain of gadgets as we do this. And then we, at the same time, we backtrack and we search for other dispatchers in the same time. Then if this succeeds, then we go to the next step, which is gadget chain simulation and verification, where each chain is simulated. So basically we check if this chain works as intended, and we do a kind of verification based on symbolic execution. Next, this chain is planted, is used to generate the payload and plant it into the vulnerable program. So this is in a nutshell what we do during attack construction. Next, I will talk about how these attacks can be crafted. So first of all, in order to craft such an attack, we have our own specification language. It's called ESL, and we have also libraries for which we have certain type of functionalities. So in order to craft such an attack, people have to import from our API using these keywords, import certain type of functions which we define there. The functionalities are defined in Python, and as you can see, we have different types of primitives defined in this Python files, like linked list, loopless, and read-write operations, execute operation, manipulation operations. So this have to be imported into the ESL specification in order to be able to craft the attack. So we have all kinds of primitives here, like for example, different API functionalities. We have dispatcher gadget types. We have read and execute functionalities. And this is how we basically reuse our API, and basically the specification can be very small. Next, these are two examples of how different primitives look in our own attack specification language, ESL. So on the left here, we have an infinite loop. So here, basically this program in the linked list dispatch, it loops from line 4 to line 6. So as you can see, we have this go to, and it loops here forever if we want to read something in a register. And then we have the conditional branch here. On line 6, we have this if the register is equal to this value, then we go to the end, else we execute this printf. So these are just two examples, but we have more of these primitives, and you can see that it's very actually easy to write such simple primitives. In total, we have more than 10 primitives, and this can be, of course, extended to other primitives if needed. Next, I show you different type of gadgets. So on the left, we have this node JStream function, which basically uses the RDE pointer and does certain type of manipulation. Here, for example, in the middle, we have the same another type of gadgets for initializing the RDX register with a arbitrary value. Here again, the RDE contains this pointer of the fake object, which is then used to further do the necessary computation. And on the right, we have the gadget used to write to an arbitrary memory address if the register RSI is below an attacker controlled value. Again, the RDE contains this pointer of the fake object. So these are 3 examples of gadgets, and of course, there are more. And basically, we use them during our attack construction process. Next, I will discuss about how this ESL statements can be mapped to machine code. Basically, we have different type of registers. We have semantic filters, and we have certain type of constraints. And then basically, The mapping is on the right. So here you see is x86 machine code, and basically the load, the read, the manipulate, and the execute operations map one-on-one to this machine code. And of course, after we define them in our attack specification, these are mapped to this machine code, which do exactly as you can see here on the right, different type of moves, calls, manipulation, register operations. And of course, this list is not comprehensive. We didn't list all our primitives here. Further details are presented in the paper. So next, in order to understand how we search for dispatcher gadgets, we have to consider the virtual table hierarchy, which is a little bit different than the class hierarchy. In C++ programs or Java programs, all object-oriented programming languages have these primitives. And here are on the right, the virtual tables and the corresponding entries. Basically, these are virtual functions which can be called at that particular level in the class hierarchy. So basically, the tree or the class hierarchy is traversed, and based on the present virtual entries there, we might find different type of dispatcher gadgets, also based on the functions which can be called from this dispatcher gadgets. So this is just a visual representation to give you an idea on how this tree maps to different type of entries in the virtual tables. So C1 here, as I said, corresponds to C1 to this node, C2 corresponds to this node, C3 corresponds to this node, and as you can see, this function 1 is inherited down the tree as one would expect due to inheritance. So next, when we search for dispatcher gadgets, we start, let's say, from the root node, and then we traverse in all direction by a depth first search approach. And then based on each node, we check if this node can be a candidate in our gadget chain. And if yes, for example, this green one, we put it in our chain, else we backtrack. And if we encounter nodes along the path which cannot be used in this gadget chain because they violate the memory constraints or the verification steps, as I mentioned before, then we basically backtrack, and all the paths which lie underneath this node would be, of course, not traversable in the virtual table hierarchy. So this is just a visual representation of what actually happens, and more details, of course, are presented in the paper. So in order to assemble a gadget chain, for example, we have here the ESL payload, we have the shell, and then basically we can do execute operation. Blue boxes represent operations which are reachable and which actually don't allow a next step. And black boxes represent operations which can be used in the chain and then have next operations which can be done afterwards. So with the black line, we identify operations linkage or continuation. And here red basically means that the red arrow basically means that from this operation, we cannot go to another execute, or basically this mean the same. So this is just to give you an impression of how these operations can be sequentially written. Next, we present you our gadget chain assembly algorithm, and it has as input it has an input the list of gadget types in order they should be called. Then we have candidates mapping of gadget types to candidate gadgets. Then the state is the program state just before the virtual function dispatched, and the result is a chain of compatible gadgets. What's important here, for each function, we have different type of targets which are visited with all the states. If state here is feasible, then basically we simulate until call site is reached again. And basically we determine in this way by traversing this nodes in the virtual table hierarchy if functions and if nodes can be added to this gadget chain. And of course we simulate it, and if in case this simulation is succeeded, then basically we add them, else they are not added to this gadget chain. Coming to the results, we ask ourselves four research questions. The first one was, how can iTOP, our tool, be used to construct control flow hijacking attacks? And for this, we used a case study based on the Node.js program. There we created different type of payloads like the shell, iLoop, and condition, and we search for different chains and demonstrate that we can generate more than 10 payloads in a very short amount of time. More details are presented in the paper. Then how much protection do static CFI policies offer after deployment? So basically here we took the 6 state-of-the-art CFI policies, which are basically published each in one top-tier security conference paper. And then we looked for all these primitives which our ESL language has, and marked the time which was needed for each for the Node.js program with all the 6 policies in place to find this particular primitive. So as you can see, the time increases the more stronger the CFI policy is. So for example, here shrink wrap or marks or VTV, we have timings of up to 5 hours and potentially even longer for searching for this type of primitives. And in some cases we didn't found them because maybe the search space was small, or we could improve our searching algorithm. Next, the next question was how much attack surface reduction is needed to effectively protect from control flow hijacking attacks. And here, basically, we devise a theoretical approach to look at this. We devise a formula in which we basically manipulate this parameter PG. And based on this manipulation of this factor, we see that we obtain different rates of surface reduction of attacks. And this is just to give you an impression of how different attack surfaces vary based on the on this PG algorithm which we manipulate. Further details are presented in the paper. Then the next question was, how vulnerable are programs with no CFI protection in place to control flow hijacking attacks? And here we took a bunch of real programs. We used a certain type of CVEs. We measured the times, and we look for different type of COPE dispatcher gadgets like main loop, recursive, and then different type of gadgets from ESL like read, load, write, and execute. And we measured how many of these gadgets were actually found. And to no surprise, the bigger the program is, like Firefox and Chromium, the more of these gadgets can be found. So as you can see here, for example, for Firefox, we found the read gadget like 120 times, 1,000 times, of course, and the execute gadget 118 thousandths of times. So there are a lot of primitives in these programs which can be used for crafting our attacks. Next, also belonging to the fourth question, how vulnerable are programs with no CFI protection in place? Here, basically, we looked for all our attack primitives and these real-world programs. And basically, what we tried here was to generate different type of payloads. And here, in case we had a check mark, we could generate a payload based on this primitive. If we had the clock representation like here, we timed out. And if the X was presented that the gadget was not available or our searching algorithm was not able to find it. So as you can see, in most of the cases, we are able to generate such a payload. In some cases, we are not able, and these are mainly concerned in this area where we have the iLoop, the condition, the for, and the C shell. further optimizations of our algorithm would definitely lead us to better results. Next, we have our discussion and limitations. So in our discussion, points which are super important to be mentioned is symbolic execution. So if our approach relies on symbolic execution for simulation and verification, so there are a lot of optimization approaches with how symbolic execution can be improved, and there are a lot of techniques which can be used and put in place in order to increase the accuracy of our search algorithm. Then we have iTOP's analysis generality. This basically means that we can extend actually our tool for other type of attacks, not COP only related attacks. In future, we have tool potential. We see that other attacks can be crafted. So as we currently operate at function level, so for us, one function is a gadget because this is how it is defined in COP. We can see potential to use other gadget at a more fine granular level. Then of course we could find more gadgets as we need them. Then gadget evaluation. In order to check if a gadget is of a certain type of it or if it's usable, here the needed approach can be improved, and we see a lot of potential there. And then with respect to COP attacks, we see a lot of also potential there and possibilities to improve our attack with respect to the COP attacks. And the approach is there to look in mostly C++ applications, which have a lot of virtual functions and dispatcher call sites. Then with respect to the limitations and future work, the gadget discovery time is quite big depending on the scenario, and this can be improved. This we plan to do in future work. Then we have the gadget search granularity, which I mentioned that can be also improved in the future by looking at more fine granular gadgets and searching approaches. And then the attack probability formula. It's important to mention that it's just a theoretical approach which helps to have a better perception of how the attack surface might change by varying different type of parameters. So important lessons can be learned there. And we have different type of attacks, which basically shows us that our tool can be easily modified, and especially the front part with ESL and attack specification can be reused very easily for crafting different types of other attacks. So in summary, iTOP is a framework for fully automatic construction of control flow hijacking attacks, which can bypass state-of-the-art defenses, as we show in our paper. iTOP automates the analysis of target binary and can build payloads under consideration of state-of-the-art CFI policies. We evaluated iTOP by testing it on several real-world programs, successfully creating different type of payloads. And we used iTOP to show that many state-of-the-art CFI policies are too permissive, and we showed how to bypass them. So in case you want to test our tool, this is available on GitHub, where we have also 4 demo videos. And if you have questions, please go ahead. Thank you very much.